Hi, in this video we're venturing to this brand new topic, entropy. So what is entropy? Entropy is a measure of molecular disorder. So it's quite abstract to thinking about how you define it. So for example, if you're thinking about solid and liquid gas, which one is more confined and which one is like the molecules is like a free roaming? Right? So solid is more pure crystal. They're lined up really in a nice array. So they are more confined. However, for gas, they are free roaming, so they are having more molecular disorder, right? So in that situation, we would totally thinking about the entropy increases going from solid to liquid to gas. So you can write it down like entropy actually have a symbol as S. S for gas is going to be greater as for liquid than S than solid for the same substance. So to define that disorderness, there is one way to define entropy. So S is equal to K times natural log P, and K here is a constant. It's called a Boltzmann Constant. And P is probability. It's like describe what's the probability of disorderness. You know, when that probability increase, you're going to have a higher level of entropy. Then what is the base level? When will entropy to be zero? And here is actually leads us to the third law of thermodynamics. They said if it's a pure crystalline and at absolute zero temperature, right? And it's in perfect order. In that situation, the entropy is zero. So that's our reference point. And by the way, we cannot get into absolute zero temperature. It's like we can approaching it, but we never get it for the third, and that's the third law of thermodynamics. So at absolute zero temperature for pure solid crystal, then they said entropy is going to be equal to zero. That's our base point. However, this definition, S equal to K times natural log P, was actually not often used for our thermodynamics. We actually have another definition. So here we go. So another definition for entropy is ds, differential element of entropy, is equal to delta Q, the heat transfer over time. And this have to be a condition internally. INT means internally reversible process. So internally reversible, that's another very ideal situation, right? If it's reversible, there's no friction. In that situation, we can integrate. From here, we can integrate delta S. It's going to be equal to final minus initial. Then we integrate from state 1 to state 2. We'll have Q over T. And write down our condition internally reversible process. Okay, so that helps us to calculate entropy change. So this is a formula for entropy change. Now let's look at one special situation. This special case is if this is first condition, if it's internally reversible, and the second situation, if it is going to be isothermal, what will be the entropy change, delta S, right? So going back to this governing equation right here, so delta S is going to be equal to state 1 to state 2. But here, isothermal, which means T is constant. If it's constant, we can take this out of our integral, so that'd be 1 over T. And then we'll have delta Q, internally reversible process. Well, what is going to be delta T integral? That will be just heat transfer Q over T. So that's our formula for entropy change if it is going to be internally reversible and isothermal process. That's it. I'll see you next time. Bye.